Okay, last time I saw y'all, this is what we were talking about. We were talking about what happens if your domain is not a rectangle when you're doing an integral. And the point was that you end up with bounds that are not constants on the inside integral. Right? So in particular, the lower bound is going to come from how well these lower bounds of the x slices are functions of x. And then the upper bound is likewise going to come from how the upper bounds on these x slices are functions of x. Right? So it's just a matter of kind of looking at the shape, and you got to make some clever decisions about which way to slice and that kind of thing, but it's usually a very process-oriented thing. And so along those lines, we did a detailed example. This is where y'all started watching the videos from last semester due to my illness. There is a process. I just want to emphasize real quick what that process is. Right? If you're looking for a particular bounds are going to come from points, identifying the appropriate point. Right? Points are on curves. So you got to look at the picture and identify what is the appropriate curve. That curve has a corresponding equation. And so this is the little connect the dots. Bounds come from points. Points come from curves. Curves come from equations. Right? And once you see that equation, okay, well then, remind yourself, what is it you're trying to find? Solve for that thing that you're trying to find in the equation that you've identified. And that's your bound. Sometimes the fish just jump in the boat. Here in this equation, the variable was already solved for. That's convenient, right? Won't always be that nice. Sometimes you have to do a little bit of work. We saw that in subsequent examples to actually algebraically solve for what you're interested in. But anyway, that's the process. I urge you to please rely on the process. Right? There's a common mistake, very common mistake that gets students get told this, or they glean this somehow in a high school multivariable calculus class that the bounds are just the equations for whatever the you look at the shape and you see the equations, that just tells you the bounds. It's not that simple. It absolutely is not that simple. You've got to watch out for things like depending on which way your differentials go, which variable are you solving for? Which bound is which of those 2 points on that same curve? These are non-trivial questions. Which order should I slice in? And there's several different considerations to go through. So again, don't take a sort of like simple-minded approach. You've got to have and of course as always in this course, you've got to have a process that makes sense, right? I did some magic in my head and got the right answer, doesn't cut it, right? So your process has to make some sense. I got to be able to see your process. Okay, all right. Certain properties of double integrals that are a pretty quick read, I think. All this is very believable and straightforward. So I'm going to let y'all read that, and some applications. So we talked about double integrals in general, and we talked about how you can use double integrals to compute volumes under a surface. But here we're observing that you can use a double integral to compute volume between 2 surfaces. Right? And it's a slightly different application of a double integral, of a Riemann sum, if you prefer. Right? But the point is, it's still a Riemann sum, and you're still inferring volume. Little pieces of volume as being heights times areas. Right? But still you're making very literally a Riemann sum argument, natural geometry, right? Just the details are a little bit different because the question's a little bit different. Okay, and then another example. This is a nice example, of course, because give me 2 seconds. Because the domain is not given explicitly in the statement of this question. Here, you have to infer what the domain is by looking at the 2 surfaces that were actually given and inferring from that what your domain is. Yeah.
How is the volume thing that you wrote up? How is that really any different from doing the integral of the top minus the integral of the bottom?
Well, algebraically, it's exactly the same.
Okay.
Right. But geometrically is really not obvious, right? Because, okay. So what a lot of students want to do is write this down immediately. And I'll point out that if you were to look at a graph of this function, that graph is not that one, and it's not that one, and it's also not on this picture. Right? Now you can, and I think maybe this is what you were asking, you can say that the volume that we're interested in here is, you argue geometrically, the difference between this volume and that volume. Now that's a geometric observation, right? But think less about the answer to this narrow question, and more about, let's try to use this as a tool for getting better at using double integrals to solve problems, right? And so, you could do this geometrically, but again, our goal, look, this is a little bit of mathematical weightlifting. The goal is not to get the weight to move around. The goal is to build the muscle, right? And so let's think about this as an excuse to use Riemann sums. Let's not try to avoid using Riemann sums. Yeah. Does that make sense? Yeah. Yes.
What if one of those graphs was like in a negative quadrant? Would the formula remain the same?
Yeah, absolutely. Yep, absolutely. Yeah. You do have to worry about, what is the actual domain. Like, so look at this problem here. So, you got to make sure that you're not computing integral over in this section where that's not part of what's on the inside. Right, so you got to make sure you understand the domain correctly. But if one of the functions happens to be negative, it doesn't matter. The point is, this height is still height, independent of whether maybe if some of the height's below the xy plane. Who cares? Doesn't matter. It's still, so think of it from a Riemann sum point of view. Doesn't matter. Right. Okay, so that was all last time. Where we I say last time. This was from the videos that y'all watched last time. Where y'all ended the videos is this symmetry theorem. So I remind you of this old theorem from single variable calculus. Right? Nice odd symmetry theorem. Neat feature that you can look at certain kinds of integrals, and if certain conditions are met, then presto abracadabra, the integral is 0. That's nice. Right? We just avoided a lot of, integration by parts and substitutions, and my gosh, right? Those things can get ugly. So pretty sweet. And we talked about why it's true. The idea, now again, we're looking at a graph here, and I always kind of feel a need to point out, okay, this is a graph. We can afford to draw a graph because this is single variable calculus, and we're no such luxury in multivariable calculus most of the time. But anyway, here we are. From this graph point of view, you can see how these terms in the Riemann sum cancel because, one of them over here and another one over here, right? This one and this one are clearly negatives of each other because, the function's odd. That's the whole point of an odd function, right? And then they pair up perfectly because the domain is symmetric. And so everything cancels and you get 0. So, we got around, we were almost to making the same argument for a double integral, and of course we do have to define some terms, etc. I got to define what does it mean to reflect through a line. What does it mean for a function to have odd symmetry over a line? This is all from the recordings. What does it mean for the domain to have a symmetry over a line? This is all just kind of ripping off and extending these ideas here from single variable calculus. Shameless rip-offs. Right? And with that said, we made this bold assertion that, again, two conditions being met, if the function that is your integrand has odd symmetry, and if the domain is symmetric, and I can't emphasize this enough, both over the same line. Got to both be over the same line, right? Then your integral is again presto abracadabra equal to 0. No slicing and dicing required. No doing the inner integral with integration by parts and substitutions and all that. No doing the outer integral with integrations and substitutions and all that. There's a lot of effort that goes into computing a double integral, and we just waved the magic wand and it disappeared in a puff of smoke. Right, so that's, again, a really nice theorem, and then we left it there. So a little bit of a cliffhanger. So here, let's finish the discussion of symmetry. The argument as to why this is true, it's just like with single variable integrals. Right? We look at a term here, right? And we look at a term here. Missed. And those terms cancel. They have negative values of each other because they are reflections of each other and because the function is odd over that line. Right? Then they all pair up in this way because the domain is symmetric over the same line. That's what makes all the terms cancel. And everybody pairs up, everybody cancels, and what's left is nothing, therefore 0. Right? So it's just a two-dimensional version of the same argument that we made for the single variable case. Okay. Side note: there's a better way to prove this result. Well, I don't know. There's a more algebraically slick way to prove this result using something called change of variables, which is a multivariable analog of substitutions. And we haven't done that yet, and we'll talk about that a little bit later on. For the moment, I want to leave you with this Riemann sum argument. And honestly, the Riemann sum argument's a little bit more sort of intuitively satisfying even. Right? So this is, I'm going to say, this is why the theorem ought to be true. Right? And then making it precise maybe is a little bit better with the later argument. Yeah. Okay. All right, so let's get our hands dirty and actually use this theorem. So let's suppose we have a domain here that is the unit square, and we've got a function here, f of x comma y equals x minus y, and now let's compute that double integral. Now this is an easy one, right? It wouldn't be scary to do this as an actual iterated integral. We could crank this out. It's not the point of this example. I just want to, let's get our hands dirty with an easy one where there's not a distraction of algebraic ugliness. Okay. Again, mathematical weightlifting, let's do this with symmetry just for the purpose of learning symmetry. Okay. So now I'm going to choose this line, y equals x. Now a very natural question to ask at this point is, how come? How come that line? This domain has lots of lines of symmetry. Not just that one, but also that one. How come I'm not using that line? Also that one. Also that one. There's several lines of symmetry. Why am I using that one specifically? I want to put a pin in that. We will come back and talk about that in a moment. For the moment, again, I just want to show you the mechanics of how to use this theorem, right? And we'll talk about the strategery next. Okay. So, mechanics. Here's our line. Y equals x. Here's a formula for how you do a reflection over that line. Now, this is a neat trick. There's only a handful of lines that you're going to need to be comfortable with doing reflections over, and this is one of them. So just make sure to remember this trick. It's a neat little observation that if you look at the line, the point x comma y, and just think about how that reflects, and think about how this little green frame reflects. Well, it's going to reflect the frame like that. Look, the x becomes the y becomes the x. Cute, right? I mean, so you notice that and remember it, and no problem. Okay, so that having been said, I'll notice that my domain is symmetric over that line. Geometric observation. I think it's pretty clear. Not much has to get said there most of the time. I further claim that this function has odd symmetry. Now, this is something that does require some elaboration. That is not at a glance obvious. Right? So we do have to actually demonstrate that it's odd, and let's remember, how do you prove something is odd? A function has odd symmetry if, when you plug the reflection into the function, you get the negative of the original value. Right? So we just got to literally plug in and confirm that this works as we claim it does. So here's my my reflection. Reflection of x comma y is y comma x. Plug that right into there. Right? Now I need to compute f of this thing. Now be careful at this point. A lot of students get a little too attached to the alphabet and don't pay attention to the purpose that the variables are serving here. When I say that f of xy is x minus y, what I mean is whichever variable is first goes there, right? And then whichever variable is second goes there. So look, if you've got f of y comma x, let's be really careful about this. Notice the first thing that therefore goes there is y. Right? And then the second thing that goes into the function, it's actually x that does what the dummy variable y is telling it to do there. Right, so do be really careful. Okay, 2 seconds. Really careful about this. A lot of students just reflectively write down, if I see x's and y's, and f of x's and y's is x minus y. That's too sloppy. Right, so be super careful. Yes?
So what if you had like a more complicated graph? Like,
well, we're not looking.
Are you just switching them because like it's a square? Or
okay, so this is my formula for reflection, because that is the reflection through that line, and I chose that line.
So if it was like 4x,
there's all sorts of other examples that we'll talk about some other examples as well. But there's a different formula for reflection for every situation. Yeah, totally. Okay. Yeah, we can't go through all of them in one example. Yeah. So let me say that differently. You have to be very careful when you look at your problem. Make sure you understand what line you're making a symmetry argument with respect to, and then infer your reflection formula accordingly. Yeah, absolutely. Okay, so there we go. F of, by the way, here's another way around this algebraic oddity. If you like, you could rewrite this function completely. Just keep in mind when you write f of xy equals x minus y, x and y there are just dummy variables, right? So you could totally rewrite this as f of like a s comma t is equal to s minus t, right? And then scratch this right off. And now when you find yourself looking for f of y comma x, now there's really no confusion. Y is s, and it does what s does. And it's just, there's no sort of like, is it x, or is it the other x, or is it the other y, or which way is right? So it's another alternative if you find this a little confusing. Okay. All right. So anyway, y minus x, which you notice is the negative of x minus y. Namely, it's the negative of the original value of the function. So as required, so this function does have odd symmetry, and therefore the integral is equal to 0. Boom. Right? No slicing, no dicing, no integrating. No fundamental theorem. Just poof. Okay, I'm a big fan. I think this is a powerful tool. Now let me pull back the curtain. Where did I come up with this clever idea of using this line y equals x? Well, so there's a certain amount of intuition and instinct that you're going to have to develop for this. You're going to have to sort of have some, like I say, experience with what are the various formulas for reflection. What do those reflection formulas? So here's one, right? So make sure to remember this one. The line y equals x is a common line to reflect over. You should know that formula. Okay. That said, look at the function that you're hoping, fingers crossed, will be odd. So you can apply your symmetry argument, right? And ask yourself, well, is there anything that I can do to this? How can I fiddle with the x and the y or the whatever and make this the negative, as it needs to be, of the original value? And you look at that and you think, well, if I'm going to make that the negative of the original value, I need x minus y I need to figure out what I can do to turn that into y minus x. And then you can realize, I can turn x minus y into y minus x by trading the x and the y. And once you realize you're trading the x and the y, you know this is your formula for reflection. And once you know that's your formula for reflection, then you can infer, reverse engineer, whatever you want to call it, the line. Right? So it goes like this. The function motivates your reflection formula. Your reflection formula then motivates your line. Often. I think this is a good way to motivate what your line of symmetry is going to be. Okay. All right. So that being said, here's some rules for how to use this theorem, this technique in this course. Let me start with what you are not allowed to do in this course. You're not allowed to do the technique that I'm going to confess that I profited from more than once in a math or physics class as an undergrad, and that is to look at an integral, have 15 seconds remaining on your exam, and think, I don't have time to do this one. Integral equals 0 by symmetry, pencil down. Right? I scored more than once doing that, right? So as it turned out, the integral was 0 by symmetry, and cool, right? Okay, so like I say, I invented that scam. Right? So keep in mind, in this course, we're not interested in answers. We're interested in reasoning. This is a class about reasoning, right? So what I failed to do in those examples way back, 30 years ago, I failed to give any reasoning, any meaningful reason. It was a total shot in the dark. I wrote integral equals 0 by symmetry, just, thoughtlessly, right? So you got to give me some reasoning. Right? So specifically, here's what I want to know. Here's what I want you to give me for me to consider that you have made a reasonable symmetry argument. You've got to tell me, what is your line of symmetry? Right? What is the corresponding formula for reflection? You have to claim and be correct that the domain is symmetric. You don't have to give me any proof on that. That's usually geometrically pretty clear, right? So, but you do have to claim it. You got to write it on the page. Domain is symmetric, because you need to recognize that you understand that is in fact important. Right? That is a requirement. So you got to put that down on the page for me to know that you realize that that's a thing, right? And you have to be correct about it. Right, but you don't have to justify it. You have to recognize and be correct that the function is odd, but you do have to give me reasoning for that. I need to see that reasoning, because there's algebra there and it's not intuitively obvious at a glance. Right? So this is what you got to give me if you want to get full credit for a symmetry argument. Notice, still not that bad, right? It's a lot less to write down than cranking out a hard double integral, as sometimes these kinds of problems might be. Okay, so make sure you give me what I need to recognize that you've made a full symmetry argument. Any questions before I go on? Yeah?
How would you do this if you constructed a line which went through the middle of this square?
Well, then we'd have a different formula for reflection. And so let's see, am I going to do one of these? I guess I don't have one of those in play. So yeah, so I'll make this is just a different sort of a little clever move that you've got to notice. So reflecting over that line, I'll point out that when you reflect this point, you get that point. Right? They have the same y coordinate, clearly. Okay? And the x coordinate and the new x coordinate, oh gosh, let me just call it x prime, will always add up to 1. So x plus x prime is 1, so x prime is 1 minus x. Yeah, so it's a slick move, right? So this is another little, now you have another little tool in your bag of tricks, and so another little, apply as useful. Yeah. Okay. All right, here's a less trivial example. And this one, you still could do this, but this would start to get a little bit annoying. But suppose you want to do this double integral here, and you've got an integrand that's a little weirder, and you've got a domain that's not going to have constant bounds. So there's going to be a component of annoyance to doing this, brute force. If you iterated integral this integral, not that great. Okay, let's start from the strategic point of view on this question. I look at this and I think, oh, this is not the ugliest domain I've ever seen. In fact, one line of symmetry leaps off the page at me. Right? But only one line of symmetry. I emphasize, this is not a line of symmetry there, right? So you cannot use the x-axis. Please be careful. Please be super duper careful when you identify a line of symmetry and you correspondingly write down the formula for reflection. So easy to get the minus sign in the wrong spot. Lots of students will say, oh, well, I'm reflecting over the y-axis, so my minus sign should probably go on the y. Nope. Right? It goes on the x. The geometry is clear. So, like I say, this is a very common landmine to step on. Please don't step on that landmine. Everybody see what I'm talking about? Everybody going to be careful with that? Okay. All right. All right. Now, what does this tell us? Does this guarantee us we can use this symmetry argument? No. We have found a line of symmetry of the domain. We have a reflection over that line, but what we don't yet know is if the function is odd. Right? So we've got to take our function here, and we've got to plug in, the usual deal. We've got to plug in the reflection. Plug in the reflection into our original function and yada, yada, yada. Go through the algebra, and sure enough, as we were hoping, we get that needed minus sign. This function does have odd symmetry. The domain clearly has this symmetry, and spike the football. Integral 0 by symmetry. And notice all the needed details are there. Okay. All right. Yep.
So in this example, there's basically only the one line.
There's only the one line that you could use. In fact, here, there's also only the one line that you could use. Right? So in other words, you cannot use a symmetry argument over that line because the function's not odd. Right? You see what I'm saying? So yeah, this is arguably a more dangerous example here because there's several sort of like teaser lines that look like you could make a symmetry argument, but you can't. Right? So yeah, dangerous. Yeah. Okay. Here's another example. Now, I'm going to be real quick with this, but same domain. So still using this domain here. And let's suppose that my function is this, and can I use a symmetry argument? And this is another landmine. I've seen some sad stories on questions like this one. A lot of students will say, "Oh, look, check it out. The whole reason that we had the oddness in this example here is because of that cube. The cube, -1 cubed, -1 to any odd power, is going to give me the -1 that I need, and there's my odd power, and so I've got oddness and I've got a symmetry, and students will say, integral equals 0 by symmetry over the y-axis, right? This is not, right? The symmetry goes the other way. Very importantly, here, in this case, the 3 is on the y. If you're saying the -1 is going to go on the y, that means you're talking about a reflection over the x-axis, and the domain's not symmetric over the x-axis. And so the argument just does not work. And in fact, said differently, if you use the only symmetry of the domain, then that negative goes on to the x, which then gets squared, and then you don't get the negative that you need. So that symmetry argument doesn't work either. There is no symmetry argument to be made in this example. And so here's the ugly part. Here's where it's really nasty, and I wish it weren't so, but I'm sorry, but this is the reality of the situation. If a student makes a symmetry argument for this question, nothing that they have written on the page is both true and relevant to the solution of the problem. Not a thing. Right? For this question, as written, a relevant solution would require slicing it up, making an iterated integral, and plugging and chugging. And the student didn't do anything resembling any of that. There's just no way in my most generous interpretations that I can give any partial credit, because there's no progress that's actually been made. And so a student would probably get a 0 on this question. So that's the danger. That's why I want you all to be really careful about symmetry arguments. They're super awesome when they work, right? But if you try to apply one thinking that it works, but it doesn't, then you've got nothing. So they are dangerous. Powerful tool, very dangerous. It's an explosive. Be careful when you're playing with explosives. This is mathematically explosive. Yeah.
So in terms of like best practice for things like exams, if we're just like not sure if the symmetry argument applies, just go with the double integral.
Sure. I mean, it's hard for me to. It depends on how not sure you are, right? I mean, because there's probabilities and expectation values, and let me say it this way. It's just very high risk, right? So if you're not sure, then maybe think through and just try to get more sure. There's only a short checklist, right? And if you don't know the checklist well enough that even thinking about it carefully during the exam, that you'd be able to be sure one way or the other, then maybe you don't know the tool as well as you should to be using it. And then, now again, it's your gamble as to what do you do on the exam. I can't make your gambling decisions for you. Yeah, but do be careful. You're playing with dynamite. Yeah. All right. Okay. Two last little quickies about symmetry. So one is, so you know why I'm such a big fan of this. I did a second major in college in physics, and physics is full of symmetries. I mean, just chock full. The world's full of circles. The world's full of spheres. I mean, it's just a tremendous amount of symmetries. So in the, 9 or 10 physics classes that I took as part of my second major in physics, I'm going to guess about 20% of the integrals that I encountered, and I think that's a conservative estimate. About 20% of the integrals that I encountered, integral equals 0 by symmetry. This is an awesome tool. Super powerful. If you do the math on that, that means a full 1.8 courses of a physics major boiled down to integral equals 0 by symmetry from a certain point of view. Right? So that's a lot, right? That's worth our talking about it for a few minutes in this course. Right? And I know a lot of y'all are engineers. It's not the same as physics, but again, engineering is full of circles. It's full of spheres, and it's full of symmetries, deliberately constructed symmetries, in fact. Right? So I think this will be a big tool, and I hope y'all will make big use of it. Like I say, I'm a big fan. Here's the other thing I want to talk about. There is another symmetry theorem. There is an even symmetry theorem. And I know y'all remember that probably from Calc 1, Calc 2, wherever. I'm not going to show y'all an even symmetry theorem in multivariable calculus. I just don't think it's worth the risk. I don't think it's worth the risk to use it. I don't ever use such a theorem myself. And here's why. When you have an odd symmetry argument, right, there's risk of, oh my gosh, did I inadvertently write down the wrong formula for reflection? But there's the huge payoff of integral equals 0. I'm done. Okay. With the even symmetry theorem, just as much risk. And the payoff is not very good. The payoff is, instead of doing an integral over this domain, I'll instead do an integral over a different domain. And, multiply by 2. You're still doing an integral over a pretty much equally, in fact, symmetrically ugly domain. It's really just as bad, right? You're benefiting maybe a little bit in avoiding a couple of minus signs, right? It's just not worth it. So I am not going to state an even symmetry theorem. As such, you cannot cite an even symmetry theorem because it's not in the book and it's not in the notes and it's not in my class and it's not therefore available for you to use. And I think I'm doing you all a favor on that, right? It's just not worth the risk. If you don't have odd symmetry, I strongly advise don't use symmetry. Okay. Okay, so we're going to go on and do some physics applications. These are pretty much straight out of the book. And there are lots of applications of multivariable calculus to physics and engineering. So we're going to do some of those. If you don't know the relevant physics from a previous physics class, no sweat. I'm just going to show you. This is a couple of little quickie things. We're not going to test you on the physics itself. Don't worry about it. But first idea I'm going to tell you about is something called torque. And the idea is that if you are supporting at a single point a rod, and let's consider a piece of mass here. Well, look, that mass is pushing down. There's a point of support, so there's going to be sort of a rotating motion, or rotating sort of impetus, whatever you want to call it. But the thing is, it's not just about how much force there is, force coming directly from mass. You can write down the mass really easily. Right? But it's also about, well, how big is your lever arm? If anyone's ever changed a tire on the side of the road, right? Don't get onto the tire with a little hand-sized ratchet wrench. Well, try it. It'd be funny, right? But you won't be able to open it with a ratchet wrench. You got to get yourself one of these big crowbars. Side note, even those are sometimes not enough, and you have to get what they call a cheater bar, which is a 4-foot-long iron pipe, right, that you then put over the 18-inch crowbar. And now you've got a huge lever arm, and it's just so much easier. You got to push much further, of course, but the torque is much more advantageous. Okay, so the length of that lever arm matters too. Okay. So that product tells you the amount of torque that's created by. Okay, so let's see here. So we have the length of the lever arm, and we have the amount of the mass. By the way, I'm going to conflate mass and force, and I'm going to assume we're on the surface of the Earth. Most of us spend most of our time on the surface of the Earth, right? Let's not worry about changing a tire on the moon. So, right. So the total amount of torque is that product, or excuse me, the torque applied by that piece. Now notice that's just for that one piece. Right? And if the question is, look, I'm supporting an entire rod, an entire one-dimensional thing, then the amount of torque applied by a single piece, well, that's not the whole story. There's also this piece over here. And there's also this piece over here. And there's also that piece there. And there's a bunch of little pieces. So no surprise, we're just going to use an integral. We're going to take the amount of torque applied by each piece, and then we're going to add up over the entire rod from A to B. That gives us an integral representing the total torque. Okay. So if you have a rod like that and you point of support and you want to compute the total torque, because some pieces are applying more torque, some pieces are applying torque the other way, right? A grand total, how much torque is there twisting the rod? There you go. There's your formula. Okay, a little bit of physics. So reasonable point that you might want to ask is where, for what value of S, is the torque equal to 0? All right, if I want the total torque to equal to 0. So this would be called a natural point of support. And that's the point where it would balance. There's just as much torque pulling it that way as there is pulling it that other way. Right? Well, no problem. Set the integral equal to 0. Nothing to it, right? This equals 0. Move things around a little bit, solve for S, and there's your answer. So that's what you call the center of mass. Sometimes they call it the centroid. And I'm going to rewrite this a little bit just for algebraic elegance. I'm going to rewrite this as integral from a to b of x dm divided by mass, but let's not forget that the mass is integral from a to b of dm. So there's something kind of elegant about this formulation that you see that this is a ratio of two integrals where the integrands are x and 1. So another point of view on this, by the way, if you've ever seen the notion of a weighted average, Maybe in a Calc 1 class, if you've seen a weighted average. This is literally the weighted average of the x coordinates on that rod. Different point of view. Okay. Another quick observation, super quick. This DM thing, don't forget, DM is just kind of a handy shorthand for density times dx, noted at the top of the page. So when you need to turn these into actual integrals, dx integrals, it's density times dx. There's something convenient about writing it as dm, though. It's a little bit shorter. Rolls off the tongue a little more nicely. Okay. So that's all single variable version. Now, this being a multivariable calculus class, let's talk about the multivariable version. Here it is. It's no big deal. And look, if you have now a two-dimensional solid of some sort, right? Some sheet, let's say, and you want to know not the point of support, but if you want to know where would I put a line of support so that the torque on either side, the grand total torque would be 0, so it wouldn't fall off. If I wanted to balance my phone, dangerous game, but if I wanted to balance my phone with a single finger like this, where is the spot, right? Well, you can still write down formula for torque. You can still add up over all the pieces, still solve for where is this x bar. It's the same argument. Healthy exercise, by the way. I encourage you to do this, right? But you can solve for that x bar just like we've done on the previous page. It's just a double integral instead of a single integral, whatever. And here's your formula for x bar. And likewise, again, healthy exercise, totally analogous. You can solve for y bar. So I encourage you all to go through those arguments, make sure that, again, the purpose of this is not to learn physics. The purpose of this is that these are good exercises in seeing how Riemann sums can apply in lots of situations. So this is an exercise in understanding how to use a Riemann sum. Okay, so give that a shot. But make sure to know these formulas. These are important formulas to know. By the way, neat double interpretation. Once you know both of those things, once you know x bar and y bar, then I argue that this is actually a point of support. If you know where the x bar line is and where the y bar line is, well, now you've got, and I'm not about to do this with my phone. I don't want to drop it, right? But there is some point that you could put your finger underneath that would make your phone balance. Please don't do this and then charge me for your phone repair, right? But that would be a point of support. Okay. Because it can't fall over in either direction, and therefore it's not going to follow. Okay. Okay, so good formulas to know. Centroid, center of mass, whatever you like. Side note, now do notice we were talking here about a mass in the plane. There is a similar notion, which is if you just talk about a geometric region in which there is no mass, and you want to talk about the centroid of a geometric region, just assume the density is 1. Any constant doesn't matter. 1's very convenient constant. Assuming a density of 1 or any constant, that'll define the centroid of the region. Okay. All right, so enough with the physics. Here's an example. Suppose you have as a domain this upper semi-disk. By the way, let me just remind you of some terminology. The term disk refers to a fully two-dimensional region. If you want to talk about just the single curve that is the boundary of that disk, the word is circle. Right, so we've got to distinguish between disk and circle. Mathematicians don't conflate these things. Okay, so here we're talking about the semi-disk, so it's a two-dimensional region. Let's find the centroid, the center of mass. So here's the formula for x bar. Just writing down the formula from the previous page. The area is easy, so 1 over the area, no problem. And we've got a double integral to compute. And good news, it's 0 by symmetry. Again, flashbacks to my college days. This happened so often you wouldn't believe it. Right? Awesome. We just saved ourselves a bunch of effort cranking out a double integral. So now I of course remind you, you have to give me details. Right? Again, I'm on to the scam. I invented the scam. Right? So you got to supply me the detail. You got to tell me what's the line of symmetry, blah, 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 like we talked about before. Okay. By the way, I want to distinguish this argument here with mathematical details describing that this mathematical construction of a double integral is zero by symmetry. I want to distinguish that from the physics argument of, well, can't you see if you just put, it's the same on both sides and so it would balance. Right? That's a physics argument, which I presume is fine in a physics class. This is not a physics class. This is a math class. You got to give me math arguments. Again, I'm not interested in answers. I'm interested in reasoning, specifically mathematical reasoning. Got to give me the mathematical reason. So you got to write down the integral and argue symmetry about the integral. So I want to make sure that's perfectly clear what the expectations are. Okay. Okay, so that's X bar. What is Y bar? Here's Y bar. Sadly, no symmetry argument. Ugh. And we're going to have to actually earn it this time. Oh, yeah, question.
I'm a little unsure how you got the denominator value for X.
Oh, yeah, so this area here is pi a squared, right? And so the area that I'm actually interested in here, I'm just interested in the semi-disk. So that's going to be 1/2 of that. Yeah, that's right. Okay, so here's our Y bar integral, and I'm going to have to crank it. And I'm going to give you two options on how to do this cranking. One is you can take this double integral, by the way, our dA, let's say it that way, and you could slice like that. Now there's details. Okay, a bunch of examples last time of how to find bounds and everything, but Y goes from 0 to A. Right, and then for any given value of y, x goes from a bound that you can solve for to a bound that you can solve for, and those are negative that square root to positive that square root. Now, details, y'all could. Okay. And then take a deep breath and plug and chug. And there you go. Now, this integral kind of works out, sort of, it's fine, you end up, when you get the ugliness, by the way, did y'all notice, in case y'all haven't, maybe you've already noticed, but whatever you have on the inside bounds, that's going to find its way into the outside integral's integrand. Right? So we're accustomed to, in single variable calculus class, saying, oh, the bounds, whatever. Who really cares about the bounds on the integral? That's just numbers you plug in at the end. It doesn't matter. They're just numbers, right? Not anymore. Inside bounds become integrand for the outside integral, and ugliness, therefore, becomes ugliness in integration, and that's real ugliness, right? So there is a cost, then, a significant cost to having these square roots in those bounds. But we get lucky, and that ugliness is offset by the fact that there's a y there, and so you can do a cool substitution and, et cetera, details. Okay. Here's your alternative. Instead of doing dx dy, you could instead do dy dx. Now, it's a different slicing, right? X now goes from negative a to a, and then for a given value of x, y starts at 0, ends at, that square root. Now, details for y'all. Crank it. Make sure you can do that. Right? Make sure you're reliably, proficiently, quickly, competently, blah, 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 able to get those iterated integral bounds. And here we get a lucky break. Check this out. Your first antiderivative is an antiderivative of y with respect to y, which gives you y squared. And sweetly, that square takes this square root and poof, right? And there's no square roots anymore. And that ugliness from the inner bounds just kind of doesn't make it into the outer integral after all. That's nice. we got lucky on this one where it, we happened to have this over here and it was, worked out nicely. But here, even better, right? This I think is a significantly easier way to solve this problem. Right? What's the more? No, of course we get the same answer either way. Right? So what's the moral of this story? I'm going to add this to your list of tools for how to decide which way to slice. If there's a preferred independent variable, okay, I think that can be a nice motivation, right? Here, there's the circle, x squared plus y squared is constant, so it's not clear which one is the preferred independent variable. There's no corners particularly either way, so those motivations that I gave you in the videos that y'all watched Monday while I was out, neither one really applies here. So here's your third consideration. Think about what your inner integrand is, and then ask yourself, what do you want to integrate first with respect to? And what might be fortuitous? See what I'm saying? So here, I look at that y, and I see that square root. That square root's just about to jump on me. And I think, wouldn't it be a cool move if I just turned that y into a y squared before the square root hits me, and then, sweet. Right? So that's a motivation for putting dy on the inside. It's just a motivation. I'm not saying it's always going to be that way and that this is always the right choice, but it's a consideration to think about. Okay. All right. And so there it ends. We'll pick up here on Friday. Y'all have a good day.